Ostwald dilution law. Ostwald dilution law is an application of the law of mass action to weak electrolytes in a solution. And as far as weak electrolyte is concerned, weak electrolytes are the solution that doesn't allow the flow of electric current. So he applied the equilibrium law to ionic dissociation of what of 1 mole of an weak acid. And Ostwald dilution law or Ostwald dilution principle is actually applicable for the weak electrolyte, not the strong electrolyte, because nearly all strong electrolytes ionize completely in the solution. Now, let's just say we have the case of the weak acid and also the strong acid. The strong acid ionizes completely in water, and the weak acid tends to ionize partially in water. The Ostwald dilution law is applicable for the weak acid. Is a law that is applicable to the weak acid because weak acid ionizes partially in water, but it is not applicable for the strong acid because strong acid ionizes completely in water. Now let's just say we have what? We have a weak acid Ha, right? We have a weak acid Ha. This Ha dissociated into, that's H plus, right? And also what? That's my A minus. In this case, my H plus is actually the acid and my A minus is the base, right? So here I'm going to have this to be in aqueous state because it is in ionic form and it is inside a solution, right? So I'm having them in my aqueous state, and I should have this one in my liquid form. Now looking at this, before the reaction, we know that the like known amount of my weak acid Ha will actually what reacted, right? Will be present before the dissociation reaction, or you say before the weak acid undergo dissociation reaction. Now I'm going to have what? I'm going to have, just let me just say 1 mole of what? Of Ha that is produced, that is involved in the reaction, and 0 amounts of this, and this is also what is known. That is before the reaction undergo equilibrium reaction, this and this amount is what is unknown. Then after that, after the dissociation reaction, right, I'm going to have, let me just say, alpha amount of this that is what that is dissociated, and alpha amount of my base that is what dissociated. This is my hydrogen ion and what and the base here. Then I will have my 1 minus alpha amount of this that will be left over, right? So at concentration, let me just say the concentration of what of my Ha, concentration of Ha at equilibrium. Now that means I'll be dividing them by what by the volume, right? So dividing them by volume, I'm going to have my 1 minus alpha divided by what the volume, right? Then here I'll have my alpha divided by what volume, and here I'll have what my alpha divided by what volume. So in this case, this is what actually the Ostwald, this is what he did. He applied the law of mass action to the equilibrium dissociation of what of the weak electrolyte. Now looking at this, applying the law of what of mass action, I'm going to have my Ka here, right? My Ka to be equal to what concentration of what of the hydrogen ion, right, multiplied by what concentration of what of the base, right, divided by what concentration of what of the weak electrolyte, which is what Ha. Then looking at this, my concentration is actually what a number of mole of a substances divided by what by the volume. That's why I'm dividing everything here by what by volume. Show that I have my Ka to be equals to what that's 1 minus alpha, right? No, it's actually what my alpha square. That's my alpha over what over volume multiply what alpha over what over volume, which are the concentration of what of hydrogen ion and also the base. So divided by, right, I'm having it to be what divided by what my Ha, which is what 1 minus alpha divided by what volume, right? So here I'm going to have my Ka to be equal to what that's alpha square divided by what V square, then multiply what my volume divided by what 1 minus what alpha, right? So this you cancel one of this, show that I will have my Ka to be equal, that's my alpha square, right, divided by what V into brackets 1 minus alpha. Then in this case, am I going to drop it just like this? No, I'm not going to leave it like this, because what Ostwald actually did is that he will try to find the relationship of the weak electrolyte to a constant degree of dissociation. That is, at constant temperature, the degree of dissociation of the weak electrolyte is going to be proportional to the root of its dilution. So here I'm going to make my my alpha, which is the degree. Alpha is the degree of dissociation. Degree of dissociation. So degree of dissociation. So I should have something like this. Making this sort of formula, I'm going to have my what? My alpha squared to be equals to what? That's Ka, right? Then multiply by what? My volume. Then multiply by my volume times 1 minus what? 1 minus alpha, right? So in this case now, since the substances I'm using here is actually a weak electrolyte, since it is a weak electrolyte, I can neglect this what? This alpha, because my alpha is less than, let me just say it is less than 1. That is, it is not up to 1. Since it is not up to 1, that means I can what? I can neglect my alpha here, since it is a weak electrolyte. And the major fact about weak electrolytes is that they actually ionize partially in water. That means it doesn't what? It doesn't donate all the hydrogen ions to water. You understand? So here my alpha is less than up to 1. It's not up to 1. You understand it down? So I can just neglect my alpha. Neglecting alpha here, I'm going to have my alpha squared to be equals to what? Ka times what? Times volume multiplied by what? 1 mole of the weak electrolyte. Right? So here, what do you think I can do here? I can just go ahead, since I said at constant temperature, the degree of dissociation, which is my alpha of the weak electrolyte, must be directly proportional to the square root of its dilution. And dealing with the dilution, that means I should have it to be my alpha square equals what? That's a root. Let me take root of both sides, right? Taking root of both sides, I'm going to a root of what? Of Ka times what? Times volume multiply what? 1 mole rather. So here I should have my what? My alpha to be equals to what? That's K root of what? Root of Ka multiply what? By V. But there is this major important fact that you need to note here. My Ka is actually what? A constant value. That means in this case, removing the K, I'm going to have my alpha to be equals to root of what? Of V. Can you see it down? So this is actually what Ostwald dilution law is all about. Alpha equals what? Equals to root of what? Of the dilution. And I can just say my alpha, no, I'm removing what? The constant. Removing the constant, I'm going to have my alpha, which is what? Proportional to what? Proportional to what? My root of what? Of V. That means at constant temperature, that is at equilibrium, at constant temperature, the degree of dilution, which is what? My alpha, it must be directly proportional to what? To the root of what? Of V, root of its dilution. No, this V multiplied by what? 1 mole. So this is just what Ostwald dilution is all about. And the thing is that the value of alpha can be calculated by measuring what? The conductance of the solution. You know, we said you are talking about weak electrolyte, and weak electrolyte, they doesn't allow electricity to pass through them easily like that, right? So the value of alpha can be calculated using alpha equals to what? That's lambda V divided by what? Lambda infinity. Where my lambda V is known as what? The equivalent. My lambda V is equivalent conductance at a particular dilution. At a particular dilution. That's my lambda V. And my lambda infinite is also what? Is also known as equivalent conductance. Conductance at a particular infinite, right? Let me just put the diagram here. Just infinite. Check it down. So I will explain what is meant by conductance and also equivalent to the conductance, the resistance. I will explain that in another video, in a separate video. But just now, the value of alpha can be calculated using what? Using your lambda V divided by lambda infinity, where this V and infinity, they actually what? The subscript of the lambda. Then that's just it. Just know that also dilution is just what? The application of the law of mass action to weak electrolyte in a solution. The application of law of mass action to weak electrolyte in a solution. So he applied what? The law of mass action. He applied using the equilibrium law of ionic dissociation. Let me just say the equilibrium constants of the ionic dissociation of what? Of the weak electrolytes. Now let's just see the question I'm having here. I'm having some question here. Now the first question I'm having here with me is that, look at this question. A 0.25 mole per day MQ solution of ethanoic acid is found to be 1.3% ionized. Calculate the value of acid equilibrium constant of the calculate the value of the acid equilibrium constant for the acid. Now look at this now. The thing is that here I need to identify the electrolyte they are talking about here. The electrolyte here is actually the ethanoic acid, right? A 0.25 mol per dmq solution of ethanoic acid is found to be 1.3% ionized. Calculate the value of the acid equilibrium constant for the acid. Now looking at this, my ethanoic acid, that's CH3, right? COH. If it's undergo our dissociation reaction, right, it's going to give that CH3 COO minus, right, then plus what, H plus. Where was my hydrogen ion and also the acetate ion is what they are in aqueous solution, right? They are in aqueous solution, and this is what, this is my liquid, which is the electrolytes. Now looking at this question very well, I just need to go ahead and do just simple thing, you know. Before the reaction, what am I going to have? Before the reaction, I'm going to have what, 0.25 moles of mole per dmq of this that is produced. Then I'm going to have 0 amount of this that is produced. Then after the reaction, then what am I going to have? I'm going to have 0.25 of this minus x. That is, my reactant is going to decrease this time, and my product is going to increase this time. That means I'm going to have x amount of this that is what that is produced. Get it right down. So what do I need to do? Before the equilibrium, after the reaction, before the equilibrium. You understand what I mean by that? After the reaction, we have this. Before the equilibrium, then I know since 1.3%, since 1.3% of hydrogen ion is ionized. Get right down. It's ionized. Since 1.3% of hydrogen ion is what? Is ionized. I can just go ahead and say that my percentage dissociation, right, equals to what? Equals to x over c multiplied by what? 100, where the x is the concentration of the hydrogen ion produced. Concentration of hydrogen ion after the reaction, while my c is the concentration of the ethanoic acid before the reaction. Now look at this now. Percentage dilution is what? That's 1.3, right? Equals to what? My x, which is unknown value, divided by what? My c, which is what? The concentration of acetic acid before the reaction, which is 0.25, right? 25 multiplied by what? 100. So here I'm going to have my x to be equals to, that's should give me something like 3.25, right? 3.25 times 10 raised power what? Minus 3. Once you press everything on calculator, you see that it is 3.25 times 10 raised power minus 3. Now let's just go ahead. It should be, that's a mole per dmq, right? So let's just go ahead. Now we just need to consider what? The equilibrium. Now at equilibrium, I'm going to have what? 0.25 minus x. What's my x? Which is what? 3.25 times 10 raised power what? Minus 3. In this case, I'm not going to neglect x. No, I'm not going to neglect the value of x, since I can see that this is the value of x here. Since the value of x is already known, I don't need to neglect it. So here I'm going to have 3.25 times 10 raised power what? Minus 3, right? And this is also what? 3.25 times 10 raised power what? Minus 3. Now let's just go ahead and apply what? And apply Ostwald dilution principle. So here I'm going to have it to be what? I'm going to have my Ke to be equals to what? Concentration of what? Of CH3, right? COO minus, which is my base, multiplied by what? Hydrogen ion divided by what? We are going to have it to what? CH3 COOH, right? So here I should be having something like my Ka should be equals to, this is actually 3.25 times 10 raised power minus 3 all square, right? Then divided by what? 0.25 minus what? 3.25 times 10 raised power minus 3. Then what's the value of my Ka, which is the equilibrium constant for the acid? The value, after pressing everything here on calculator, you should have something like 4.28 times 10 raised power minus 5 mole per dmq, right? So that's just the answer. You should have something like this. Now let's just move to the second question I'm having here. The second question here says, is 0.55 mole per dmq of ammonia solution is found to be 0.58% ionized. Calculate the base equilibrium constant for the dissociation of the base. Now looking at this question, it's actually very simple. It's just similar to the first one, but the first one is actually talking about the acid, and while this one is talking about what? A base. And the base here is actually what? The ammonia solution. And you all know that ammonia is a base, right? It's going to accept a proton, right? Because all base, they actually serve as proton acceptor. And in this case, that means I need to react my ammonia with what? With water. Reacting with water, I'm going to have what? My NH3, right? The initial reaction is going to NH3 plus what? Plus H2O. To give what? To give, here I'm going to have my ammonium ion produced plus what? OH minus. But since the constitution of water is since water, can you say water is a constant? Yeah. Since water is a constant, that means I need to negate the constitution of water. So that I'm going to have my final reaction to what? NH3, right? NH3 in what? In that's liquid form. Should be looking from exactly plus what? Let me just say water is constant. Let me just write it with plus aqueous. We are going to have it to be what? To be equal, to be in equilibrium position with what? With that's NH4 ion, right? In aqueous state plus what? Plus OH ion in what? In aqueous state. So in this case now, the question now says a 0.55 mole per day MQ ammonia solution is found to be 0.58% ionized. Calculate the base equilibrium constant for the dissociation of the base now. So the first thing is that before the reaction, what am I having? Before the reaction, I can see that I'm having what? 0.55 mole per day MQ of what? Of ammonia solution rather. It's found to be what? To be 0.58% ionized. My degree of dissociation is known as what? Percentage ionization, which is what? Alpha. That's what? 0.5%, right? So in this case now, I'm going to have zero amount of this that is produced, right? Then after the reaction, I'm going to have what? 0.55 amount of this minus X, which shows that my ammonia will decrease with time, right? And I'm going to have X amount of this that is produced, X amount of this is what is produced. Then, since I know that 0.58% of what? Of the solution is what? Is ionized, right? Is ionized. So since 0.58 is present is what? Is ionized, then I'll still go ahead and use my what? My percentage dissociation cost what? That's X over C multiplied by what? 100, right? So here my percentage is what? 0.58 equals what? X over C. What was my C? Concentration of what? Of ammonia solution before the what? Before the reaction, which is 0.55 multiplied by what? 100, right? So here my X is going to give me the value of what? Of that's 3.19 times 10 raised to power minus 3. You press everything on calculator, you are going to cross multiply here. You're going to have your X will equals what? 0.58 multiplied by 0.55 all divided by what? 100. So your answer is should be 3.19 times 10 raised to power minus 3. Now let's just go ahead and come back. Let's just come back to the question here. I'm going to have before, after, and also what are in equilibrium. At equilibrium now, I'm going to have 0.55 minus X, which is what? Minus 3.19 times 10 raised to power minus 3 of ammonia is what? Is at equilibrium with what? With this is actually what? 3.19 times 10 raised to power minus 3, and this my OH hydroxide ion here is 3.19 times 10 raised to power minus 3, right? So now let me just go ahead and use apply Ostwald dilution law here. Applying it here, I'm going to use my Ka. What's my Ka? My Ka is equals to what? That's concentration of what? Of ammonium, right? Times what? Hydroxide ion, right? Divided by what? Ammonia solution, which is NH3. So I'm going to have my Ka to be equals to what? Everything here should give me 3.19 times 10 raised to power minus 3 all square, because this is 3.19 and this is also what? 3.19 times 10 raised to power minus 3. That's actually what? All square. Divided by what? Ammonia. Ammonia solution is what? That's my 0.55 minus 3.19 times 10 raised to power minus 3. So here solving this, you are going to have your Ka to be equals to 1.861 times 10 raised to power minus 5. So that's just the answer. Just the major important fact that you need to note here is that as far as Ostwald dilution law is concerned, it is not applicable for the strong electrolytes. It is mainly applicable for the weak electrolytes. Why? Because weak electrolytes they ionize partially in water. You understand it now? So now let's move to the last question here. The last question here I'm having here with me is actually somehow different from the one I've been solving. Here the question says find the percentage dissociation and hydrogen ion concentration. That means I'm asked to find two things. The first one is what? Is my alpha percentage dissociation, which is what? Degree of dissociation. Find the percentage dissociation as what? Hydrogen ion. My hydrogen ion, right? Concentration of 0.2 mole per the MQ ethanoic acid. If the dissociation constant of the acid is 1.85 times 10 raised to power 5, so here I'm giving my what? I'm giving my Ka to be equals what? 1.85, right? Times 10 raised to power minus 5 mole per the MQ. So you get it right now. So let me just try and just use the first thing is that to get our alpha, which is the degree of dissociation, we can just apply what Ostwald dilution law here. Applying Ostwald dilution law, we are going to have alpha to be equal to what root of what of kV, which is Ka times V. So I'm applying this alpha equals to root of what of Ka times what times V. Shall you get right? And but in this case, I don't know the value of what of B, but I actually know the concentration of the what of the weak acid to be 0.2 mole per dm³. So the concentration is what concentration equals what that's number of mole over what over volume. And as far as Ostwald is concerned, the mole that we are talking about here is what is 1 mole. That is 1 mole over what over volume, which is concentration equals what 1 over what 0.2, right? Sorry, my concentration that's 1 over volume, which is 0.2, right? Equals to what? That's 1 over what over volume. So here I'm going to have my volume to be equals to what? That's 1 over what 0.2. So having it to be 1 over 0.2, my answer, my volume equals what? That's 5 dm³, right? So coming back here, my alpha equals what? Root of what? That will be root of 1.85 times 10 to the power what minus 5 multiplied what by 5. So I'm going to have my alpha to be equals to what? That's 9.62 times 10 to the power what minus 3 mole, right? That's my alpha, which is the degree of dissociation. Then I just need to convert to percentage dissociation from the amount I know. No, I'm adding 9.62 times 10 to the power minus 3 is the amount that dissociated. Now I need to convert to percentage dissociation. That means in order for me to calculate the percentage dissociation, that means I need to convert to percentage dissociation. So converting to percentage dissociation, I'm going to have my percentage dissociation, right, equals to what? That's 9.62 times 10 to the power minus 3, then multiply with 100%, which is equals to what? 0.96%. So my percentage dissociation is what? Is 0.96. That's just the first case. So the percentage of what of the weak acid that is ionized is 0.96%. Now let's just move to the second case. The second case says that I should calculate the hydrogen ion. Calculating the hydrogen ion is very simple. I can just go ahead and say my concentration of hydrogen ion using the same relation here. My hydrogen ion is what? Alpha over V, right? So I can just use my hydrogen ion equals to what? That's alpha over what? Over V, which is equals to my alpha is what? 0.96, or let's just say 9.62 times 10 to the power what? Minus 3, right? Divided by what? V. What's my V? My V is the 5 dm³, which is my this is actually mole, right? Over dm³. That's actually my alpha, concentration of hydrogen ion. So calculating the concentration of hydrogen ion now, I'm going to have this divided by this, which is 1.92 times 10 to the power minus 3 mole per dm³. So that's just it. So you can feel free to drop more question on this aspect. I'm going to solve a lot of questions for you guys, and you will have a better understanding on it. So looking at this, that's just everything under Ostwald dilution law. Just know that Ostwald dilution law is just the application of the law of mass action on the weak electrolyte or weak electrolyte solution. So, and it is mainly applicable to what? It is mainly applicable to weak electrolytes. And the fact behind this is that the degree of dissociation, which is our alpha, is directly proportional to what? To the volume or to the root of the dilution. Just say root V, root of its what? Of its dilution. And the thing is that weak electrolyte, they obey Ostwald dilution very well. That is, they obey Ostwald dilution fairly well, yeah. But the strong electrolyte do not obey this law. So because the reason they didn't obey is that the strong electrolyte, they actually ionize completely in water at every concentration. That means, and if they ionize completely, that means my alpha won't be less than or approximately to 1. But here is going to be what? My alpha equals to 1. And if you recall, if my alpha equals to 1, from the conductance of the strong from the conductance of the electrolytes, I'm going to have my alpha to equal to that's lambda V divided by lambda infinity. And if this is equals to 1, if my alpha equals to 1, that means my lambda V divided by lambda infinity, that's actually they will be equal. That means lambda V will be equals to lambda infinity, which is in the case of strong electrolyte. That's the reason why Ostwald dilution principle or Ostwald dilution law is not applicable to strong electrolyte, because the value of the degree of dissociation is equals to 1. But in case